There is a famous curve called the Cissoid of Diocles that can be used to solve some of the three problems of antiquity. And I want to show you what it is and then what the polar equation for it is and how you derive that. So here's what it looks like. It's this sort of V-shaped thing. That is the Cissoid of Diocles, and it actually keeps going, but it goes like an it goes towards this asymptote, so it never reaches this horizontal line. Here's the way it's defined. We have a circle. The circle is centered here, in this case, at 0, 5. Or at 590 degrees, if you like polar. And its radius is 5 also. So we have that blue circle. And then we have on top of the circle this horizontal line, which in this case is y equals 10. Now what we do is we pick a point on the circle, anywhere on the circle, and then we make a line segment connecting this bottom point to that point. And then we continue until we reach that line. Now this distance between the circle and the line, that will be a certain length, and it will depend on where I pick the point on the circle. Like for instance, if I picked this point on the circle, then we would go here, keep going, and in that case, this yellow line would be longer. So what do? Well, you take this yellow length and you find a point on, so that one end point is at the pole, so that this length, I'm just going to say this is point O. I want to get point P, let's call this Q and R. I want to get point P so that OP and QR are congruent. So right here, I would have this fairly small yellow line. So we'd have this small length here. And I would make a nice blue point right here at the end point. That point is a point on this cissoid. That second line, that had a sort of larger space between the circle and the line, this yellow one. If I copy that length onto this line starting at O, it would end around there. Now I get a point there. Now it gets a little confusing when, let's say I continue this line, and I pick something that has kind of like a big slope like that, small slope, however you want to look at it. Now I'd have this really large yellow line. My QR would be really big. So when I come back over to O and try to make P so that OP is the same length as QR, it's going to end up, I'm going to use a different color for it. It's going to end up something like that. And that's going to be the point on the cissoid. And the cissoid turns into this shape. And I can do the same thing on the other side. And I get this sort of, it's like a bird flying a little bit. It looks like that. Now, to get the equation of the cissoid, it's convenient to use polar coordinates. So what I like to do is I take a random point on the cissoid, and I call that point R comma theta. So R is this green length over here. That's not green. That's R. And theta is over here. And one thing I know for sure in this picture is that this big long line segment is 10. So I need to create an equation with R, for R equals, it's going to be in terms of theta, this 10 is likely to be involved. And it's pretty tricky until you realize that by the definition of the cissoid, this line over here is also equal to r. And that's the r I'm going to find the equation for. That's going to be easier. So I'm actually even... by the way, there's also a theta because of alternate interior angles. There's a theta here. Why don't I write this r out here? So that's r, and that's theta. Now, I'm going to draw one more line, which is going to be this one. That makes this triangle here is inscribed in a semicircle, so that's a right angle. And there's yet another theta in this picture, and it's over here. And this is because this theta down here is complementary to this angle, but so is this one. So there's a lot of thetas in this picture. Ironically, the theta that I don't even need to worry about anymore is this one. Let me put some letters here. O, call this P. This isn't the same Q as before, but I'll just call this R, call this capital R up here, not to be confused with lowercase. Let me not call it R then, let's call it S. And I'll call this point Q, just to name it something. Oh, it is actually the Q from before. So here's the relationship. R, which is SQ, SQ is this line segment. Well, it's equal to the difference between SO and OQ. And maybe those two things are easier to get separately. For SO, let me just draw what I've got going on here. Here's S, here's O. Let's call this T up here. So with SO, if I don't know what that is, I'm just going to call it SO. The relationship would be sine of theta equals 10 over SO, or SO is 10 over sine theta. Now OQ, which is, make this blue, that's OQ. If you want to see what this other triangle looks like, TOQ, it looks something like this. It's got the 10 here. So I'll just call this OQ. And that I could do the sine relationship on this other triangle, because here's theta. So sine theta equals OQ over 10, or OQ equals 10 sine theta. That's the answer. Now, if this was not a diameter of 10, if it was like a D, the only difference is that these things would be Ds also. So that's the equation of a cissoid. The equation is R equals D over sine theta minus D times sine theta, where D is the diameter of the circle. You want to factor out the D? You're allowed to. You want to write 1 over sine as cosecant? No rule against that either. And that ends the video on the equation of the cissoid of Diocles.